Okay, it is class time, so let's go ahead and get started. Well, we finished up cylindrical coordinates, and so I wanted to jump in to spherical. I guess before I want to make a few announcements. Um, if you're using the practice exams or the old exams from the exam archive, there are some differences in the test material that takes place. So we're only doing, chapter 12. So if you see things like surface area integrals or line integrals, we're not doing those until the final exam because they've done a slightly different order for the material. Also, I'm going to have to move my office hours from Friday morning to tomorrow morning. So if you want to ask me some exam questions, come in tomorrow morning rather than on Friday morning. Okay, so let's jump in with 12.7. Where we're going to talk about spherical coordinates and triple integrals in spherical coordinates. So spherical coordinates are defined again by an ordered triplet. Let's kind of sketch out our x, y, z Cartesian and kind of a precursor to this is physicists and mathematicians kind of disagree on the definition for spherical coordinates. So if you're looking at a physics book, you might see a slightly different thing. For this class, we're going to use, of course, the math way. So we're going to have rho, theta, and phi. So the way to do this is kind of almost draw the same type of thing that we were doing in cylindrical. So we're going to draw a straight line down. And then we're going to have a line that comes out from the origin in the xy plane. But we're also going to have a line that comes out from the origin out to this line. So the angle from the z-axis to this line that connects the origin to our point is measured from the z-axis down. And this is phi. So this is z, y, and x. The angle, oh, I wrote a z, x. The angle from the x-axis to this line in the xy plane is theta. The magnitude of the distance from the origin out to the point is our rho. So this is a radius in spherical coordinates. This is what they typically write as rho. I'm not even going to tell you how the physicists do it because I don't want you to get confused. This is what we're doing. So in terms of x, y, and z, we say that x is rho sine phi cosine theta. We have that y is rho sine phi sine theta. And z is equal to rho cosine phi. So this is how to translate x, y, and z to spherical coordinates. It's also worth noting that rho squared is x squared plus y squared plus z squared. It's very typical to define that rho be non-negative. So typically, we say that rho is non-negative as well as have phi go from 0 to pi. So in our definition, the ranges for the angles go from 0 to pi for phi, and then 0 to 2 pi for theta. The reason for this is when, let's say we wanted to make a sphere. Well, if we started from up here and we went pi down, and then we went theta goes all the way around, we would recreate one sphere. If we went ahead and said phi went from 0 to 2 pi, as well as theta going from 0 to 2 pi, we would double draw a sphere. So typically we say that phi goes from 0 to pi. Okay, so integrating. A spherical wedge is defined by rho, theta, and phi triplet where all three are bounded by constants. So it's just like a cube in spherical coordinates. It's a spherical cube. So just like we've done before for volumes, if we wanted to approximate the volume of an object, before we used these cubes and added them up. Same thing here. If we want to do a volume in spherical coordinates, we'll use these spherical wedges. And if we do that, we find that dV is equal to rho squared sine phi d rho d phi d theta, where these are in no particular order. They all show up. But the thing to note here is that we have this extra term. Don't forget. So just like in cylindrical coordinates where we had that extra r that showed up, in spherical coordinates we get this extra rho squared sine phi. So if I were to write using the same region E, if I were to write the same or the triple integral over E of some f of x, y, and z dv, we can write this as the integral from C to D, the integral from alpha to beta, then from A to B of f, and then I have to translate all of these. So this is rho sine phi cosine theta, rho sine phi sine theta, and rho cosine phi. And then we have our extra rho squared sine phi d rho d, what did I write? That's theta. D theta d phi. So we can't forget this rho squared sine phi whenever we're doing integrals in spherical coordinates. And of course, we learned how to do general regions in Cartesian coordinates and kind of the equivalent for cylindrical coordinates. So it's no surprise that we can do without these spherical wedges in spherical coordinates. So let's do an example. Let's evaluate the triple integral over some region E of 16 z dv, where E is the upper half of the sphere x squared plus y squared plus z squared is equal to 1. So first, let's write out what this region E looks like in spherical coordinates. So a sphere should be pretty easy to kind of describe in spherical coordinates, right? It's kind of where it gets its name from. So if we look at this equation, this x squared plus y squared plus z squared, we can note that this left-hand side is just equal to rho squared, right? That means that the radius of this sphere is 1, and we already kind of knew that. So we should figure out right away that if we're going from the origin out to a radius of 1, we start to draw the inside of the sphere. But now let's get our angles correct. So if we're looking at the sphere, I'll try my best to draw a sphere here. So we have the bottom of the sphere, maybe like this. And then we have the top of the sphere, something like that. We have to think about our definition for phi and theta. Well, phi, remember, it's measured from the z-axis. So if I'm going out in rho from 0 to 1, and I also need to start from the z-axis, and I need to make out this entire half right here. So I need to come down. So I go from 0, and I make a 90-degree angle. So I need pi over 2. So phi goes from 0 to pi over 2. Then I need to worry about what theta does. So I go out from 0 to 1. I also go down from 0 to pi over 2. And then for theta, I need to go all the way around the sphere. So this goes from 0 to 2 pi. And that makes us a half sphere. It's maybe worth trying to rewrite this in terms of different segments of the sphere, like the bottom of the sphere, the left in the y or in the xz plane, or the right or the left and right in the yz plane instead. See if you can rewrite these and then like double check. Those resources are probably really easy to find online, or you can ask me or a TA. Okay, so now let's continue with this problem. So then we have that our triple integral over the region E of 16z dv We have our triple integral here. We go from 0 to pi over 2 in phi. We go from 0 to 2 pi in theta. And we go from 0 to 1 in rho. I have my 16. And then I rewrite z in terms of spherical coordinates. That's a rho cosine phi. Then I can't forget my extra terms. I have my rho squared sine phi d rho d theta d phi. Okay. So we can use a trig identity to kind of help us out here. If I have that sine of some angle times cosine of some angle, I can rewrite this as 1/2 sine of 2 times that angle. So I have a cosine and a sine here. So we can rewrite this as 0 to pi over 2, 0 to 2 pi, 0 to 1. And then we have this half that gets generated. So we have 8 times a rho cubed. We have a rho and a rho squared here. Then this cosine sine becomes sine of 2 phi d rho d theta d phi. That looks easy enough for us to integrate. So this is equal to 0 to pi over 2, 0 to 2 pi. Then we integrate over rho, and we end up with just 2 sine of 2 phi d theta d phi. There's no thetas in here, so integrating over theta is pretty easy. So this is 0 to pi over 2 times 4 pi sine of 2 phi d phi. We can integrate this, get negative 2 pi cosine of 2 phi evaluated at phi equals 0 and phi equals pi over 2. This just leaves us with 4 pi. And that's this volume integral over 16z. So in fact, the upper half of this sphere is a spherical wedge, right? Its definition were all constants, right? 0 to 1, 0 to pi over 2, and 0 to 2 pi. So this is a spherical wedge, and it's the most easiest thing to kind of describe using spherical coordinates. And this would be a major pain if I wanted to do this in Cartesian coordinates. So you can see the appeal of trying this new coordinate system. Okay, let's try another example. We're going to find the volume of the upper region D that's cut from the solid sphere where rho is less than or equal to 1 by the cone phi is equal to pi over 3. So I'm going to first draw out, we have a sphere of radius 1, and what I'm going to plot this on is the z and xy plane. So I have a sphere of radius 1, maybe something like that. And then I cut it with the cone phi is equal to pi over 3. So that means I have the constant angle pi over 3. But remember that this can get revolved around. So it's not just one line, it's the cone with angle pi over 3. So it looks like this area here is my region D. And of course, this thing is getting revolved around in theta. So it kind of looks like an ice cream cone, right? It's got this cone-like fashion, and on top of it is like a big sphere scoop. So now let's kind of figure out how we can represent this in spherical coordinates. It's actually a spherical wedge, right? But let's kind of figure it out. What's going on here? Let's draw. So if I look in my rho direction, I go from the origin all the way out to the edge of the sphere, no matter where I am. The cone doesn't do anything for rho because it sits exactly along the direction that rho will take. So it still goes from 0 all the way out to the edge of the sphere, which we found was 1. So rho goes from 0 to 1. Okay. In order to make this object in theta, we have to go all the way around. So theta goes from 0 to 2 pi. And that leaves us with phi. So phi goes from the z-axis all the way down to the cone. And we don't have to worry about this segment over here because that's going to be drawn when we rotate this segment here all the way around in theta. So there's actually 2 ways we could have done this. We could have gone from this side to this side and then had theta go from 0 to pi, or we could go from the center here all the way down and go from 0 to 2 pi in theta. So since we already said that theta is going from 0 to 2 pi, we're going to say that phi goes from 0 to the edge of that cone, which was pi over 3. So this is another spherical wedge, and our volume is 0 to pi over 3, 0 to 2 pi, and 0 to 1. Can't forget my sine phi and my rho squared. D rho, d theta, d phi. So we can integrate this. 0 to pi over 3, 0 to 2 pi. We can do the rho pretty easily. This will give us a 1/3 sine phi, d theta, d phi. Theta is pretty easy, doesn't even show up in our integrand. So this is the integral from 0 to pi over 3 of 2 over 3 pi sine phi d phi, or negative 2 pi over 3 cosine of phi, evaluated when phi is equal to 0 and phi is equal to pi over 3. This ends up just giving us pi over 3. So like we've been doing with these projections onto a certain plane, we've been drawing these objects and then kind of fiddling around and then drawing these lines that come out. So for spherical coordinates, I highly recommend that you try drawing a z versus xy plane or some equivalent of that. Sometimes you see a z versus r. So it plots what it looks like in cylindrical coordinates, but it wants you to do it in spherical coordinates. So in spherical coordinates, you would only have this right-hand side of the cone. So it'd be z versus r. And from that plot, we would need to figure out how to do this in spherical coordinates. So highly recommend drawing slices like this and figuring out what my row needs to be. And you always draw a line from the origin out to something. So it's the lower to upper bound in this radial direction out from the origin. Then you can think about what phi needs to be by kind of drawing these sweeping angles. And then if the object is symmetric in the theta direction, meaning I just draw this as a revolution around, then theta typically just goes from 0 to pi, unless it's cut somewhere, maybe it's half of this. Okay, so let's do another example. Let's write a integral that is in terms of Cartesian coordinates in terms of spherical coordinates. So I have this integral that I'll set equal to I. It goes from 0 to 3, 0 to the square root of 9 minus y squared. The integral from the square root of x squared plus y squared to the square root of 18 minus x squared minus y squared. My integrand is x squared plus y squared plus z squared dz dx dy. And I want to get this integral into spherical coordinates so that I can evaluate it. Okay. Oof. So this looks really messy in Cartesian coordinates, but let's figure out what's going on. So I always like writing our bounds down. So I know that y goes from 0 to 3. I know that x goes from 0 to the square root of 9 minus y squared. And I know that z goes from the square root of x squared plus y squared to the square root of 18 minus x squared minus y squared. Okay. So remember, the latter two integrals define our projection. So let's take a look at what our projection looks like. So this is x and y. Well, x goes from 0 all the way out to x is equal to the square root of 9 minus y squared. Well, this is x squared plus y squared is equal to 3 squared. So that's a circle of radius 3. But notice that I chose the positive version of this radical and that it's x equals this. So this is the right half of a circle of radius 3. So let me go ahead and put a circle in here. Kind of center it at the origin. So we're at the right half. But there's a reason why I only drew our axis like this, because if we notice, y goes from 0 to 3. So it's only non-negative values of y up until 3. So if x always goes from 0 out to this square root of 9 minus y squared, but then the range of y is only 0 to 3, I'm only talking about the quarter of this circle here. So that's what the projection looks like onto the xy plane. Okay. So now let's take a look at these z-bounds. Actually, before we do that, I want to go back to our projection because let's get this over with. If we look at our projection, we know that the theta is measured from the x-axis out, and it exists in the xy plane. So this tells us what theta needs to be. So thus, we have that theta goes from 0 to pi over 2. Okay, so now let's look at these z-bounds. First, we look at z is equal to the square root of 18 minus x squared minus y squared. We can write this as x squared plus y squared plus z squared is equal to 18. But remember that x squared plus y squared plus z squared is rho squared. This means that rho is the square root of 18. And remember, we typically say that rho is non-negative, so we can throw out the negative version of rho here. So we're just looking at the square root of 18. Okay, so that's a little piece of information. So now let's also look at z equals the square root of x squared plus y squared. So we knew that this is a quartic surface from way back when, and you might not remember what it looks like, but this is the upper half of a cone. And we can kind of actually figure that out by converting this into spherical coordinates. This was really easy to convert to spherical coordinates. This, however, we need a little bit of work. So let's go ahead and plug in our definitions for x, y, and z in spherical coordinates. On the left-hand side, we get rho cosine phi. On the right-hand side, we get the square root of rho squared sine squared of phi cosine squared of theta plus a rho squared sine squared of phi sine squared of theta. But notice that both of these terms share a rho squared sine squared in common. And then they have a cosine squared plus a sine squared of theta. So we can rewrite this as the square root of rho squared sine squared of phi. Well, rho we said is always positive. We can pull that out. And then we have sine of phi. Because remember, phi goes from 0 to pi, so sine on that interval can't be negative. So we can also just take the square root and not have an absolute value. So now that I have rho cosine phi is equal to rho sine phi, the rho's cancel. And what I can do is divide this cosine over. So on the left-hand side, I get 1. But on the right-hand side, I get sine phi over cosine phi, which is tangent phi. And when is tangent equal to 1? When phi is equal to pi over 4. So I kind of foreshadowed that, you know, sometimes the bounds don't necessarily give us information like one for one. So our z bounds gave us a piece of information about rho as well as a piece of information about phi. It wasn't that z gave us the rho bounds and y gave us the phi bounds and x gave us the theta bounds. It's a combination of all of them that we need to kind of figure out. We need to look at each bound separately and kind of figure out what's going on. So the cone starts at phi, or sorry, not phi, rho equals 0. Right? So what's kind of going on here is maybe let's draw this time we're going to do an R versus Z plot. Now remember, in the XY plane, our projection still looks like this. So we have to keep in mind that theta goes from 0 to pi over 2. But let's say we took a slice maybe somewhere in the middle here. What does this look like? Well, we know that phi is pi over 4. So we can just draw that in like this. And then we know that rho is the square root of 18. So it generates a sphere of radius 18. So it does something like that. So from here, we know that we're going from rho equals 0 out to this sphere equation, which was just the square root of 18. And then our phi goes from 0 all the way down to pi over 4 here. So with that, we can rewrite our integral bounds we go from 0 to pi over 4 in phi, and we go from 0 to pi over 2 in theta, and then we can rewrite the square root of 18 as 3 times root 2. And then we're doing d rho, d theta, d phi. This is also a spherical wedge. It looks super complicated in Cartesian coordinates, but in spherical coordinates, we're just looking at the spherical wedge here. We're going to have a rho squared sine phi. And then remember, we also had an integrand. So let's scroll back up here for a second. And let's look at our integrand. It was x squared plus y squared plus z squared. Well, that's just rho squared. So we have a rho squared here. So ultimately, we can just write a rho to the fourth. So we rewrote this very, very messy Cartesian integrals in terms of spherical coordinates, and it worked remarkably well. Okay. So now let's do, why don't we actually take our 5-minute break right here, and then we'll come back at around 1:30. Okay, for our last example, we're gonna do kind of maybe a blast from the past from Calc 2. So we're gonna have some improper integrals. In Cartesian coordinates. Like this. So we're going from negative infinity to infinity in both, or in all of x, y, and z. So this is all of R3. So we're trying to add up all of this function over the entire domain of R3. Okay, doing this in Cartesian coordinates, we're not going to do that. So what we can think of is, how do we convert this to spherical coordinates? If this is all of R3, well, it should be an infinitely dimensional, or a sphere of infinite radius, right? A sphere of infinite radius covers the same amount, all of R3. So what we can do is just translate this into a spherical set. So to make a sphere, remember we're going from 0 to pi in phi, 0 to 2 pi in theta, and then to cover all of R3, we need to go from a 0 radius out to an infinite radius. Then we have the square root of x squared plus y squared plus z squared. So that's inside a rho squared, but rho is positive here. So we can just write just rho for that term out in front. And then we'll have e to the negative rho squared. And then we chose the order d rho, d theta, d phi. And all of a sudden, this looks a lot more manageable than the integral that we have up here with 3 improper integrals. Now we only have this one improper integral. So first, let's do the rho integrals separately. I do. I forgot it. I got so sidetracked with how exciting this is. We do need the extra term in here. Rho squared sine phi. I even have it down on my paper. I just got so excited about talking about improper integrals. D theta, d phi. Thank you. We would have immediately hit that in the next line too. So let's look at the this rho integral here. So we go from 0 to infinity of rho cubed e to the minus rho squared d rho. Okay, and if you remember from Calc 2, doing improper integrals, we write this as the limit as some parameter goes to infinity from 0 to that parameter of rho cubed e to the rho squared d rho. I can do a u substitution, so I can let u be a rho squared So this means that du is equal to 2 rho d rho. Or that 1/2 du is equal to rho d rho. So if I look in the context of my integral here, I can set this as e to the negative u, and then I can take one of these rows and the d rho and turn that into a 1/2 du. I'm left over with a rho squared, but from this right here, I know that rho squared is equal to u. So I can write this as the limit as b goes to infinity, the integral, and we'll worry about the bounds in a second, 1/2 u e to the negative u du. Okay. So now let's talk about the bounds here. When rho is 0, u is 0. So I get 0 here. When rho is b, u becomes b squared. Okay. So how do we do this integral? Well, this is integration by parts. I'm not going to bore us too much with integration by parts. It's not really going to be tested on the exam, but it is an integral technique that we've learned in Calc 2. I'll just write out what happens. We get the limit as b goes to infinity. We're capable of pulling out a 1/2. And then we have negative u e to the negative u evaluated at 0 and b squared plus the integral of 0 to b squared of e to the negative u du. So this here, this term ends up vanishing because when u is 0, this whole thing is just equal to 0. When u is b squared, you can do just 2 L'Hopital's to figure out that this also goes to 0. This exponential beats out this polynomial every time. So this whole term ends up going to 0. So then we just have this integral that's left. So this is the limit as b goes to 0, 1/2 negative e to the negative u evaluated at 0 and b squared when we do out this integral here. We can go ahead and plug in our limits and we end up with just 1/2. So we're not done yet, but the takeaway here is not this u substitution or this integration by parts or even these improper integrals. It's the power of spherical coordinates by easily translating something from Cartesian that is a good fit for spherical coordinates. So now that we know that the rho integral is just 1/2, we can go back to the rest of our integral. This is 0 to pi and 0 to 2 pi. We have our 1/2 from our rho integral. We still have our sine phi d theta d phi. It's pretty easy for us to do the theta integral. We go from 0 to pi, and then we just get a 2 pi times this, so it cancels with this 1/2, so we can just get a pi times sine phi d phi, which is negative pi cosine phi. Phi equals 0 and phi equals pi. This just leaves us with 2 pi. Crazy. We have this triple integral over all of R3 in Cartesian coordinates, and it's disgusting. There's no way that we're going to do this in Cartesian coordinates. But by translating to spherical coordinates, this was the big step that we should be like taking away from this, right? It's very easy for us to do just a set of one improper integral, right? And then we did have to do a u substitution. We did have to do an integration by parts. We kind of glossed over, but here it kind of showcases why spherical coordinates can be so powerful in comparison with other coordinate systems. Of course, there's always a good coordinate system, right? So if you have some object, your first kind of guess should be, what do I need to be choosing versus Cartesian, cylindrical, or spherical? And we have a question here. What would the giveaway for choosing cylindrical versus spherical be, having z in the integrand as well? Or does the analysis go deeper than that? You meaning if we had a z that would be inside this integrand now, or something else? The reason why I chose spherical for this is because I saw a lot of x squared plus y squared plus z squareds. If I had an extra z in the integrand, I would still do spherical. We would just have another, we'd have to substitute that z in for spherical. So I don't think adding an extra z in this integrand would throw us off too much. It would make finding the rho integral and the phi integral, and actually all three of them, just a little bit tougher. But it wouldn't change what coordinate system it meant that would be the go-to. So it's definitely a combination. So you meant in general, not just for this specific problem. If you have a z in the integrand for anything, I don't think it necessarily changes how difficult it is in any one particular coordinate system. The way that I kind of decipher what coordinate system is best for R3 is foremost the bounds. The bounds of the integral are what I should consider the most important for integration, right? And then the integrand. So maybe I choose a coordinate system that is really appropriate for the bounds, and then the integrand gets a little bit messy, and then maybe I'll reconsider. But I will always choose the coordinate system based off of the bounds that I had. So let's kind of scroll up here for a second back to our other example. I look at this guy, right? And I've had a lot of practice, but this is kind of what my train of thought is. I look at these z bounds, so I notice that z goes first, and I see this as a sphere, right? This is z equals the square root of 18 minus x squared plus y squared. We saw below that meant a sphere of radius square root of 18, right? So I see a sphere. I immediately, it's like, okay, maybe spherical coordinates is good for this. I have this sphere right here. I scroll down a little bit, right? Maybe you don't know that this is a cone right off the bat, but you can do a little bit of work to show that it's a cone. And then I'm like, oh, a cone tells us phi. So these two already suggest to me I should be looking at spherical coordinates. Well, what does the projection look like? The projection is the latter two, so I know it's in the xy plane. And I look at these later two bounds. Not too bad. I immediately pick up that this is a circle, right? So I'm like, okay, there's a circle involved, and it's a circle of radius 3. Boom, here's a 3 here. So it looks like this looks like something like a quarter circle, right? Just from these two bounds. And then if I have a quarter circle in the xy plane, and I know that I have a sphere and a cone, I'm choosing spherical coordinates. Now, of course, this was kind of cherry picked because this is a perfect example to do spherical coordinates in. But you can kind of get some practice. Maybe you try to write this thing in cylindrical coordinates. You can. It's messier, but you can do it, and it's good practice, actually. So maybe instead of trying to evaluate these integrals, you translate them back and forth between the three different coordinate systems. And in fact, get some practice with rearranging the ordering of some of these differentials. So if you're in cylindrical, instead of doing dz dr d theta, maybe try dr dz d theta instead. Instead of doing, this is a spherical wedge, so no matter how you orient it, it's going to work out. But look at some of the older exam problems and see if you can rearrange the integration order, get an idea of what's going on. Okay, so with that, that's my rant about what kind of coordinate system to choose. That ends 12.7. So let's go ahead and talk about 12.8. Let's go to a new page here. .8 is change of variables. So at this point, we should feel pretty confident about u substitutions, right? Well, this idea extends to multiple integrals. We can do a u substitution for higher dimensional things. So first off, let's kind of revisit what a u substitution means in a single integral. So if I go from a to b, and I have f of x dx, I can rewrite this as the integral from c to d of f of g of u prime of u du. So that's a u substitution, right? You have some u variable and it allows us to translate what x is, and dx translates to g prime du. Right? Another way to write this is c to d of f of x as a function of u, right? Basically, that's what we're doing. Dx du du. So this concept extends to higher dimensions. So what are we comfortable with already from Cartesian coordinates? So if we have x and y and we're looking at double integrals, so let's kind of make a little subsection header. So we're doing double integrals. We've already learned about polar coordinates, right? We learned that if I wanted to do an area integral over some region D of f of x, y, dA, we rewrote this as f of r cosine theta, r sine theta, r dr d theta. But this looks eerily similar to what we've written up here, right? We've substituted in f a definition for x and y, and then perhaps we have some extra term that gets generated. So Cartesian to polar coordinates is a really simple example because the region that we're integrating over doesn't change, right? Notice that I have D here and I have D here. But in the 1D case, maybe it's not necessarily true that my bounds stay the same. Cartesian to polar is really nice that way. Any point in Cartesian translates to the same point in r and theta. So what if there's a transformation that doesn't preserve this? Maybe I go from some region D to some new region that we'll call maybe S. So there's some transform. So now more generally, consider a change of variables given by the transform that we'll call T. And it goes from the UV plane to the XY plane. So if I take this transform, that's a function of two variables, and I input U and V, I get X and Y. So it takes some coordinate U and V and gives us a new coordinate in X and Y. And maybe we can write out that X is equal to some function of U and V, as well as Y as a function of U and V. So for the most part, we're going to assume that T has continuous first order partial derivatives. You don't really need, you can just assume that whatever I'm about to say is true. So if I have the point T, or I use the transform on some point U1 and V1, and I get X1 and Y1, then the point X1, Y1 is called the image of the point U1, V1. So now we're going to do some definitions. If no two points have the same image, then the transform T is called 1-to-1. Meaning that for every 1 point in UV space, I get 1 point in XY space, and vice versa. So I can't have 2 points in UV space that point to the same point in XY space. So for every point, there's a unique point in the other one. If T is 1-to-1, it has an inverse transform. that we write as t to the negative 1. From xy to uv. Okay, what am I talking about? Let's draw a picture. So imagine that here I have UV space, and I've got some object. Maybe this object doesn't look necessarily the same, but it's still some coherent object, and now this is XY space. So now I have maybe some region S, and I have some region R. And I've got some point here, U1, V1, and maybe I have some point here, that's X1, Y1. So I might have the transform go from UV space to XY space, and I have the inverse transform to go back, right? So if I plug in this point into, and I use it with the transform, I get over here. And maybe I'm capable of going back with the inverse. And for every point in here, I have a unique point over here and vice versa. So if I have another point here, I only get one point over here, and I can keep doing that. So I can fill in all of the points here with all of the points here if they're all unique. So this gives us a way of kind of translating what it means to do a transform and get maybe an area integral. If I wanted to know the area of this thing, and I have a transform that has unique points to a new space, I can calculate the area of that new thing instead. And maybe my transform remakes that shape into something a lot nicer. Maybe I have a amorphous blob on this left, but I'm able to write this as maybe a square on the right. Wouldn't doing the area of a square be a lot easier? And that's why we do U substitution, right? We make the integrand something a lot easier to deal with, right? The bounds might change. It's a different interval, and that's exactly what's happening here. It's just higher dimensional now. So how does this transformation work? So what I want to do is, how do we kind of figure out how this works under integration? So we're going to draw another picture here. And of course, we're always going to do rectangles. Rectangles are super easy to work with. So imagine I've got some rectangle here. And we're going to see how this rectangle changes under our transform. So if this is U and V, I have that this is the change in V, and I'm trying to take as small of a rectangle as possible. And here I have the change in U, right? And what I can do is I can write out the coordinates of each of these points on this rectangle. This is maybe U0, V0. Up here, I have U doesn't change, but now I go up by a delta V. Over here, I have a U naught plus delta U, V naught. And then up here, I have U naught plus delta U and a V naught plus a delta V. So now we're going to try to figure out how these rectangles transform into the other coordinate system. So the edges of the rectangle will change giving a distorted rectangle. In XY space. Right? So maybe it's not so nice that this rectangle changes to another rectangle. It might be the case, but let's assume the worst and that it becomes a distorted rectangle. So first, what we can do is we have to notice that these points still need to be connected in some fashion. Right? So let's look at each of these points. So first, the point x0, y0 is when we translate u0, v0. So if my x, y coordinates get transformed in this way, maybe I can write a vector. Oh, we're back to vectors. So I have an r vector that's a function of u and v. And when it gets translated, remember we said that x was a function of u and v. Well, maybe now under this transform, I can write it as g of u and v of I hat plus how the y coordinate gets transformed, which was via our function h of u and v in the j hat direction. So basically all we're doing is just keeping track of how the x and y coordinates of this vector change. So this is the image vector of any point u and v. If we want to approximate the area of our distorted triangle or rectangle, with a parallelogram. So maybe in XY space, we have a distorted rectangle, maybe something like this, right? Where it still has these points, but now the edges kind of get morphed, right? Well, what I can do is I can still take this single point down here, and I can have a vector that points in this direction, and then I can have a vector that points in this direction. This is r of u v naught that points out to this thing here. And then I'll have some b vector and some a vector from there to get me the vector that points maybe to this spot here, which is the vector u naught v naught plus delta v, and r of u naught plus delta u v naught. So we have some vectors that originally pointed to the corners of my rectangle here. And now in XY space, I have some new vectors that point, that kind of gets in the way, to these new things. I can find A and B from these vectors, right? If I take this vector here and I subtract this R vector, then I'm going to get this A vector, right? And then I can do vice versa to find this B vector. Well, if I have these two vectors, I can approximate with a, let's do this. We can approximate with a parallelogram that consists of those vectors and find the area of this thing. Right? Now it's not great because we cut out some of this section here, but if we decrease the size of our original rectangle and we keep going and going and going and going, then this process becomes more and more accurate. And you can kind of see where we're going here. When we did this before, we kept getting more and more accurate until in the limit we became exact. This is the same type of scenario. We're going to approximate the area of this rectangle translated into the new XY space by a parallelogram. So we say that the A vector was R of u naught plus delta u v naught minus R at u naught v naught. And we said that the B vector is R of u naught v naught plus delta v minus R at u naught v naught. And maybe you see it coming. It starts looking familiar what this might look like. Well, if I have the vector A and I divide it by some change in u, this is approximately the u derivative of R. So let's actually write it with partials, not to not get confused. If I have B divided by some change in V, this is approximately how R changes with respect to V. But remember that the partial u derivative of R is GU HU. Now remember, we're saying that X is equal to G of U and V, and Y is equal to H of U and V. We can likewise just call these X as a function of U and V. Partial X, partial U, and partial Y, partial U. And then we'll have R of V, which was GV or HV, which is now partial X, partial V, partial Y, partial V. Okay, so now what we can do is approximate the area of that parallelogram with these derivative functions. right? These are vectors, right? So the area of our parallelogram is the magnitude. So let me back up here for a second. We have that A is approximately the change in u times the derivative with respect to u, and B is the change, is approximately change of v maybe times this derivative of v. All we're doing is just multiplying over these denominators, right? And the area of a parallelogram we found is the magnitude of the cross product, if you recall. So this is the change in u times partial r partial u crossed with delta v times partial r partial v, which is partial r partial u crossed with partial r partial v in magnitude times the change in u times the change in v. We're almost there. So let's actually calculate out this cross product. Well, I'll just use the shorthand definition here, just to save us a little bit of time. Let's actually do out this cross product. We have I, j, and k. We have partial x, partial u, partial x, partial u, or sorry, partial y, partial u. And then partial y, partial u. And then partial y, oh, these should be partial v's. And this should be an x. I'm messing up this whole bottom here. Let me just rewrite this. This is partial x, partial v, partial y, partial v. And then our z component was both 0 in those vectors. So we can do this cross product out. But notice the way that we write this, if I look at my x hat component, or my I hat component, I will end up with 0 because I have the 0 times a 0. For j, I get these two and these two, so I'll end up as again with 0. So the only thing that survives is the determinant of partial x, partial u, partial y, partial u, partial x, partial v, partial y, partial v in the k hat direction. So if I take this thing in magnitude, this is just a unit vector, right? So I'll only end up with the absolute value of this determinant. This determinant is called the Jacobian. Of the transform. So if we have some information about how x and y relate to u and v, we can define the Jacobian for 2 dimensions as j of u and v is equal to the determinant of partial x, partial u, and then down here with partial y, partial u, partial x, partial v, and partial y, partial v. Or we can just say this is x sub u, y sub v, minus x sub v, and y sub u. And what is the Jacobian useful for? What was this telling us? Why did we do all this work? Well, it says that the area is approximately, for our rectangle, is approximately the absolute value of our Jacobian times the change in u times the change in v. Okay, so how does that help us with this transform? Well, if our transform is 1-to-1, then what we could do is we can have some double integral in R of maybe x and y dA. I might be able to translate this into UV space and write it as some double integral on some new region S, f of x as a function of u and v, y as a function of u and v, times the absolute value of my Jacobian times du dv in no specific order. It's just now in UV space. So perhaps we have an integral in xy space that's really hard to do. And I give you a transform, or maybe you find a transform where you say that x is equal to u plus v, or maybe u minus v, and we have some other definition for y. All we need to do is figure out what this new region S is, and we can look at our Jacobian here and how it translates. So basically the Jacobian is how these dAs translate with respect to different coordinate systems. And then we just do this integral in UV space. It seems really complicated. I know we went through the whole proof and it might be a little bit overwhelming at first, but let's just do a quick review of polar coordinates. So for example, in polar coordinates, we have that x is equal to r cosine of theta, and y is equal to r sine of theta. Now, for polar coordinates, we know that r and s are the same. It's the same region. It doesn't morph at all. It's just another way to express the same ordered pair. But here we have that x is a function of r and theta, and y is a function of r and theta. So what if we just happen to take this Jacobian? Right, so I take the Jacobian, and now it's r and theta. So this is partial x, partial r, partial y, or sorry, partial. Oh, now I've gone ahead and messed up my ordering. This is going to be partial x, partial theta, partial y, partial r, and partial y, partial theta. So if we do this out, well, we take the r derivative, we get cosine of theta. And then we take the theta derivative and we get r negative r sine theta. And then here we take the r derivative, we get sine of theta. And then we take the theta derivative and we get r cosine theta. Well, we can do this determinant out pretty easily. This is r times cosine squared theta plus, because we have this negative here, r sine squared of theta, which is just r. This is where that extra r comes from. So you remember that I can write dA in Cartesian coordinates, dx, dy in no specific order, but in polar coordinates, I can write this as dr d theta in no specific order. This r was that Jacobian all along. That Jacobian was sitting there without us really knowing. We found it by doing these polar rectangles, which is how we first got this r to appear. And that's perfectly fine. That's justified. But here we can justify it by using this transform, right? If we convert Cartesian to polar coordinates, it's the same region, but our Jacobian is just r, and that's where that extra r jumps in. And you can imagine that all of the extra factors that we've put into cylindrical and spherical coordinates are Jacobians in higher dimensions as well. Okay, so with that, we've gone through the proof. We've seen the extra r coming in. Tomorrow, we're actually going to be doing a lot of examples to get us through this substitution. I think it makes a lot more sense when you start doing these examples. The proof is a little hectic, but yeah, you've at least seen it now. You don't need to remember it if you don't want to. But now we're going to start actually doing the application of these transforms. So until then, goodbye. Stay safe. I will see you tomorrow. Just a reminder that I'm moving my office hours from Friday morning to tomorrow morning. So if you want to jump in tomorrow morning, I'll be around to answer homework questions or exam review questions, stuff like that. Okay, take care.